All right. Lesson 6.5 is going to take a look at two shapes that we've spent some time talking about, but we're going to focus specifically on trapezoids and kites. Just a quick review. Remember that a trapezoid is a shape formed by having one set of parallel sides. So if I have one set of sides parallel like so, with two intersecting or connecting legs, that's referred to as a trapezoid. And a kite is defined as having one set of adjacent sides congruent and another set of adjacent sides congruent. So opposite sides are not equal here. Opposite sides are not parallel, but adjacent sides are congruent. That's what makes up a kite. The first example or vocab definition word we have to look at today is what's referred to as base angles. The base angles of a trapezoid are formed by the corresponding base and intersecting legs. So if we look at this particular trapezoid, we know that this trapezoid has two bases. This would be considered one of the bases, and this side down here would be referred to as the other base. Remember, the bases in a trapezoid are the parallel sides. The two parallel sides would be considered the bases. When we start talking about base angles are formed, as the definition says, by a corresponding base and the intersecting leg. So those two angles here and here would be considered one set of base angles. And if we go to the other base up here and we look at the intersection with the leg here and here, we form these other two angles, also referred to as base angles. So base angles kind of come in pairs. These two angles right here would not be considered base angles together. These two angles are formed by this leg. These two angles would be supplementary, but those would not be considered base angles. If this is a leg over here, we know that this is also mathematically referred to as a leg. Trapezoids. The base angles of an isosceles trapezoid are congruent. Now, we need to make sure we pay attention to probably the most key word here, and that's this, the idea that we have an isosceles trapezoid. So if I have this trapezoid, remember that an isosceles trapezoid, again, is going to have one set of parallel sides, but because it's isosceles, we have the legs equal to one another. So in an isosceles trapezoid, both sets of base angles are going to be congruent. So this angle here is going to be congruent to this angle here. And similarly, this angle up here, the other set of base angles will also be congruent. Again, notice that if I look at this angle here, this is obtuse. And the other set down here was acute. So we have to be very sure that we don't mark those two congruent because obviously they are different types of angles. If we wanted to extend this a little bit further, we could say that these two angles right here would be considered supplementary. They're not equal, but they are supplementary, which we learned means they add up to 180 degrees, or they total together 180 degrees. So base angles in an isosceles trapezoid are congruent. The next thing to take a look at is the diagonals. Much like our rhombus and kites and rectangles, we are going to explore the diagonals of an isosceles trapezoid. So again, this specific trapezoid needs to be isosceles, meaning we have one set of parallel sides. You'll notice I'm drawing this rotated on purpose. But here are our bases. They're parallel. The other set of sides, the legs, are going to be equal. And if that is the case, then we can conclude that the diagonals will be congruent. So from point A to B and from point C to D, if I wanted to label A, B, C, D, I could say that AB is going to be congruent to, not AB. AC is going to be congruent to BD. So diagonals in an isosceles trapezoid, again, emphasis on the fact that this does need to be an isosceles trapezoid, are congruent. Mid-segments of trapezoids. The length of the mid-segment is equal to the average of the two parallel sides. Now, we'll go over this in a lot more detail, but just to fill out this definition, we're talking about an average, and the two parallel sides are also known, as we just discussed, as the bases. Now, a mid-segment in a trapezoid is a segment that connects midpoint of one side to the midpoint of the other side. So in order to be a mid-segment, we need to know that both point A and B here are midpoints. So A and B are midpoints. If I wanted to take a look at the length of this segment AB, a mid-segment, or the length of a mid-segment, is going to equal base 1 plus base 2 divided by 2, which is the average. So we're simply going to add up the two bases, this being one of them and this being the other. We can add those measurements up and divide by 2 to find the average, and the average is going to be this length of the mid-segment. We'll take a look right here on a new slide. So if I have this particular trapezoid, it does not have to be an isosceles trapezoid. It could be any randomly drawn or horribly drawn example like I have here. As long as I know that this is indeed a mid-segment, meaning those two are equal and these two are equal. If I have the bases, let's say this is 4 and this is 6. Actually, to maybe help our example here, I don't want to use 4 and 6. Maybe I'm going to use 4 and let's make this 8. It might not be drawn to scale, but the mid segment is going to be the average of those two. So if I take 4 plus 8 and divide that by 2, I end up with 12 divided by 2, which is 6. And that tells me that the length of this mid segment is going to be 6 units long. So we'll use that formula later on to find the length of a specific mid-segment. Remember that a mid-segment is simply the average of the bases. Kites. Moving on to our next shape, we had trapezoids before, and now we are discussing kites. So in a kite, remember, as I described earlier, we have adjacent sides congruent, no opposite sides parallel, no opposite sides congruent. But the diagonals of a kite have a special property. The diagonals intersect or cut one vertex to the opposite vertex, and similar concept here, vertex to opposite vertex. The diagonals of a kite are perpendicular, much like the diagonals of a rhombus. So if I wanted to look at this using notation, we would know that these diagonals all intersect at 90 degrees. That, again, will be true for all kites, much like it was for all rhombus and all squares. So all we have left here is a few examples now. I'm not going to spend a ton of time going on examples. You'll get some practice on IXL. We do need to pay attention in this example to the fact that we're working with an isosceles trapezoid. So we know that this leg is congruent to this leg by definition of isosceles. So by definition, those are equal. We learned today that base angles in isosceles trapezoids are equal. So the measure of y also has to be 156. And we learned that x and w have to add up to 180. So if I take 156 and I add angle w, it has to equal 180 degrees. So subtracting 156 tells me that the measure of angle W is equal to 24 degrees. So we end up with 24 down here as well as 24 down here because base angles are congruent. So these two corresponding pairs, if I wanted to underline, are congruent as well as these two pairs of base angles. Looking at this spider web, it asks us to find the measures in angle or trapezoid ABCD. So we're focusing in on this trapezoid. I guess we're going to use a couple different properties here of shapes. If I look at the spider web, I look at this straight line as being 180 degrees. And we can see that that straight line is split into triangles down here. We have 1, 2, 3, 4, 5, 6 triangles. So if I take 180 divided by 6, I end up with 30 degrees. So I know that this angle right here is equivalent to 30 degrees. Now, if I focus on this triangle as a whole, there's 180 degrees in a triangle. We know one of them is 30 degrees. This triangle would be isosceles. So we could take 180 degrees minus 30 degrees for a total of 150. We divide that by 2 and we get 75 degrees. 75 degrees is going to be each one of these base angles. So the measure of angle A and the measure of angle B are both 75 degrees. Remember that in an isosceles trapezoid, these two angles are supplementary. So if this angle here is 75, in order to add up to 180 degrees, we would need 105 degrees there. So those two are supplementary. They add up to 180. So in summary here, we have the measure of angle A and the measure of angle B are both equal to 75 degrees. And finally, the measure of angle C and the measure of angle D are equal to 105 degrees. So using a few different properties here, but our main emphasis is on the fact that these base angles A and B are congruent, as well as C and D. Similar concept here. Just very quickly, if this is 70 down here and we do have an isosceles trapezoid, base angles, corresponding base angles are congruent. Again, we can find this missing measure by understanding that these two angles in here have to add up to 180. So if this is 70, I would need another 110 degrees to total 180. And our isosceles triangle theorem tells us that this other angle Q is also going to be equivalent at 110 degrees. Going back to the idea of a kite, diagonals are perpendicular, so I know that these intersections right here would all be 90 degrees. So the measure of angle 2 is equal to 90 degrees. One of our theorems said that the diagonals, in this case, RT and SU are going to be perpendicular. I could use the fact that 2 is equal to 90 degrees. So this angle here would also be 90 degrees by definition of perpendicular lines. We know that there's 180 degrees total in a triangle. So the measure of angle 3 is going to equal 180, take away 90, take away 72, which leaves us with just 18 degrees. So the measure of angle 3 down here would be 18 degrees. We already have the measure of angle 2, which just leaves us with the measure of angle 1. The measure of angle 1 is going to correspond to 72 degrees here as well. So the measure of angle 1 is also 72 degrees. Similar concept here. I'm just going to jump over this. If you want to use this as an extra example, feel free to come up with those missing measures on your own, discuss them with a partner. This is really the last important slide of the day. It goes back to the idea of a mid-segment. So in this diagram, we know that SX is one of the parallel sides is 7. And we know that TW here is 13. So what we need to figure out is we need to figure out, okay, if that's 7 and that's 13, what is UV going to be? Well, if we call this X, basically what we'd have to do is we'd have to find the average. So we're going to take 7 plus X. We have to divide that by 2, and that's got to equal 13. So if I want to solve this equation using algebra, I can multiply by 2 here, multiply by 2 there. This cancels, so 7 plus X equals 26. This is supposed to be X, not 6. 7 plus X equals 26. Subtract 7, and we end up with X equals 19. So our other base here would have to be 19 in order for this mid-segment to be 13. Now, we can look at kind of a unique pattern here. If this is 7 and I go from 7 to 13, I added 6 in this case. And going from 13 to 19, I would need to be consistent and add 6 there as well. So there's a couple different ways to do it, but just remember that your mid segment, which is this center segment, is going to be the average of the two bases. So we could double check 7 plus 19 is indeed 26. You divide that by 2 to find the average, and you do end up with 13. Looking at one last example, we're talking about diagonals here. We are given the fact that AC is 4A plus 2. That would be this whole diagonal is 4A plus 2. And we're given the other diagonal 7A minus 55 for BD. But if this is indeed an isosceles trapezoid, which we're told, these two need to be equal. So 4A plus 2 has to equal 7A minus 55. We can use some algebra to solve here. We're going to subtract 4A from both sides. We're going to add 55 to both sides. That ends up with 57 is equal to 3A. So we would end up dividing by 3, dividing by 3 to come up with our answer. When we divide by 3, in this case, we end up with A is equivalent to 19. So 57 over 3 is equal to 19. So A is 19. If we wanted to find the actual measurement of one of the diagonals, we would have to remember to plug this back into A, but in this case, that's not what it asked. It just asked us to find the measure of A, or the value of A, so A is equivalent to 19.